These two planets are gracefully orbiting around their centre of mass. Thanks to the triumph of modern science, we can predict their paths into eternity. But all it takes is one more planet and it quickly descends into chaos. Our magical power of prediction fails. This is the Achilles heel of physics that math cannot solve. Better math is not the answer. We need to look beyond it to find the machine code. For millennia, time was something we measured using sundials, water clocks and calendars. But we couldn't use it. Nature was described using geometry. For the motion of planets, you stacked circles on top of circles. The Greeks had perfect formulas for shapes. They knew the area of a circle or the edge of a triangle. But those are formulas for space, not for time. This worked for the heavens because they repeated in perfect periodic cycles. But for the complex reality of Earth, geometry failed. We needed a language that could describe change, not just cycles. Then, 400 years ago, Galileo, Kepler and Newton gave us something magic. The power of prediction, the power to skip time. Their major breakthrough was to capture dynamics. Newton wrote equations that described how physical quantities change from one moment to the next. Technically, these are differential equations or equations of difference. This in itself was a triumph, but a differential equation only tells you how things are changing right now. It's like walking in the dark with a flashlight. You can only see one step ahead. You still have to walk through all the steps to find out where you end up. For example, imagine firing a cannonball. The differential equation tells you how gravity is pulling it down at this exact second. But it tells you nothing about where it will be in 10 seconds, or where it will land. To find that out, you have to calculate every single step. But Newton's second stroke of genius was to find a way to sum up all those future steps, without having to calculate each one. For the cannonball, you can see this visually. If you plot its velocity over time, the total distance is the area under the chart. Analytically, this technique of summing up all the future changes into a neat formula is called integration. For the cannonball, the neat formula is called the range equation. Now, if you wanted to know where it lands, you no longer needed to track the flight. You simply plugged in the values, speed and angle into the formula, and boom, you have the destination. This was like turning on the floodlights and having a map. So, if you could write down the differential equation, the laws of change, and you could find a solution using integration, bingo, you had the shortcut to jump ahead in time. Newton called his method the calculus. It wasn't just abstract math. We had cracked nature. We could model the world using differential equations, find the solution using integration, and predict the future. This led to global navigation, the Industrial Revolution, and our modern world of bridges and skyscrapers. However, the chaos of the three planets we saw at the start, that is where prediction failed. The differential equations still worked perfectly, but there was no neat solution, no formula. The shortcut failed. The moment that the third rock was introduced, the exact solution became impossible to find. This is the famous three-body problem. It's the same physics that gave us the moon landing, but it failed the moment we tried to track just 3 rocks in space. Its implications go far beyond the motion of planets. Our most successful theories suffer from the same problem. Einstein's general relativity only has exact solutions for the simplest of cases. Quantum mechanics can only be solved analytically for the hydrogen atom. Add just one more electron and you are left with simulations, approximations and the hard work of calculation. This reveals a deep structural truth about our universe. Our inability to find exact solutions isn't due to mathematical difficulty, it signals a fundamental limitation. Think of reality as raw data. Solving the differential equation is like a zip file that compresses time and space into a pattern that we can read like a map. However, the three-body problem tells us that these islands of certainty and predictability live on the edge of an ocean of complexity and uncertainty that resists compression. To understand reality, we need to understand the origins of complexity. Math is a higher level language which provides us with some amazing tools, but to understand the operating system of the universe, we need to find the machine code. The answer turns out to be shockingly simple, and it begins with a tiny one-dimensional digital pattern. Clues began to appear in the 1980s. Stephen Wolfram wasn't looking at the stars. He was looking at the simplest code imaginable, called Cellular Automata. Imagine reality stripped down to its core, a simple one-dimensional line of digital cells, each one either black or white. Time progresses in discrete steps, row by row. Crucially, the rule governing how the next row is painted is incredibly local and simple. Each cell looks only at its immediate neighbours, and a local decision is made based on that tiny input. This is a minimal program. The established scientific intuition had always been that simple rules produce simple behaviour. And for many cellular automata, that intuition holds true. For instance, if we pick a rule and start with one black cell, the resulting pattern might expand predictably, perhaps forming a uniform triangle. The formula to predict its shape, or the colour of any cell after a million steps, is easily derived. The shortcut exists. Now look at this rule. This is Wolfram's Rule 30. In particular, look closely at the sequence of pixels down the centre column. This sequence seems perfectly random. In fact, it passes every test for randomness we have. It is a generated chaos that no equation can predict. The sequence of the centre column resists any known analytical description. No elegant formula can be found to predict the colour of the cell at step 10,000, let alone 1 million. It is perfectly deterministic. The rules are simple. If you ran this code 1 billion times, you would get the exact same pattern 1 billion times. Yet, to know the colour of that central cell after 1 million steps, you must simply run the program step by step, all million steps of it. Wolfram gave this limitation a name, Computational Irreducibility, and its implications are profound. When a system is computationally irreducible, it means there is no logical shortcut, no closed-form analytical equation, and no compressed mathematical formula that allows you to bypass the act of simulating the system step by step. To know the answer, you must perform the work. This is the three-body problem in a simple computational form. The system itself is its own shortest path to the answer. The chaos of Rule 30, a pattern born of the simplest possible digital rule, forces us to accept an astonishing conclusion. Complex behaviour does not require complex rules. Instead, complexity is the inevitable result of often simple rules running an irreducible computation. These discoveries inspired Stephen Wolfram to write his 2002 book, A New Kind of Science, and later to launch the Wolfram Physics Project. His goal was to demonstrate that the computational paradigm is the fundamental basis for science. Our inability to find neat solutions for the three-body problem, fluid turbulence, and even the second law of thermodynamics are not failures of math. They are simply systems that resist compression. But this raises a big question. If the underlying fabric of the universe is this irreducible chaos, why then has our scientific revolution been so successful? The answer, Wolfram observes, is humbling. The history of science has been the history of finding the islands of order. Understandably, we have spent much of our scientific endeavours mapping the specific, safe pockets of the universe where the shortcuts do work, where the complexity cancels itself out. We've built our bridges, our rockets, and our theories on these islands, but we ignored the ocean of complexity surrounding them. Accepting this ocean of complexity also restores the meaning of time. If there were a mathematical shortcut for everything, the future would be solved instantly. Your life would be a pre-calculated formality. But computational irreducibility says no. It implies that the only way for the universe to build the future is to run the program. Time is not just a coordinate, a parameter, or a reference frame. Time is the calculation. The passage of time is simply the universe doing the computational work. But if the universe is a computation, where is the hardware? What is the substrate that it is running on? For millennia, we have assumed space was a continuous, smooth, empty sheet. But what if, similar to matter and light, the fabric of space is actually discrete. But that is a subject for another video. If you made it this far, please leave a comment and consider subscribing. If you'd like to find out more about Stephen Wolfram's work, I've added some links in the notes below. Also, as a footnote on the three-body problem, in case you are now wondering about our own solar system, thanks to the Sun being over 99% of the total mass, our solar system can be approximated as a series of two-body Sun-planet systems with relatively small perturbations from the other planets. It's still chaotic on a timescale of millions of years, but thankfully not on the scale of human lifetimes. Thanks for watching.